Yes. Now we will derive the Nernst equation for single electrode potential. In 1889, Nernst is a scientist. He derived an equation which gives the relationship between single electrode potential and standard electrode potential through a concentration of metal ions at a particular temperature. As in the last class we have discussed that is single electrode potential, or we can say electrode potential and standard electrode potential, right? So what is electrode potential or single electrode potential? Is the electrode potential, that is the potential difference developed between the electrode and the electrolytic solution through a concentration of metal ions. And what is the standard electrode potential? When the electrode is in contact with the solution of unit concentration of 298 Kelvin temperature. The measured potential is said to be a standard electrode potential. So here Nernst derived an equation which gives the relationship between a single electrode potential and standard electrode potential through a concentration of metal ions at a particular temperature. That is, in 1889, Nernst derived an equation which gives the relationship between E. What is E here? Single electrode potential or electrode potential, that is denoted by capital E. Relationship between E, that is electrode potential, and standard electrode potential through concentration of metal ions. So now first we will consider the reversible redox reaction, right? Consider a reversible redox reaction. As I told you, what is redox reaction? Is the reaction at which the oxidation and reduction reaction takes place simultaneously. So consider a reversible redox reaction. Here Mn plus metal ions plus N electrons. That means metal ions gets reduced by N number of electrons, and we are considering a reversible reaction. So this is the indication of reversible reaction which gives rise to metal. Okay, here we are considering a reversible redox reaction, that is metal ions gets reduced by gaining of N number of electrons and gives rise to metal. And according to law of mass action, for this particular reaction we can write the equilibrium constant. That is, so here equilibrium constant. How do we denote equilibrium constant? Kc. Kc is equals to molar concentration of product by molar concentration of reactant. So here in this particular reaction, which is product, that is metal, molar concentration of metal by molar concentration of metal ion, that is Mn plus. So Kc is equals to, according to law of mass action, molar concentration is denoted by it is written in square bracket. That is molar concentration of metal to molar concentration of metal ion. Right? So consider this is the equation 1 or Kc value. That is Kc value or equilibrium constant. Right? And now, according to thermodynamics, we know that the decrease in free energy gives the maximum amount of work done in a system. Right? So, according to thermodynamics, which relates the maximum amount of work done in a system. That is, we write according to thermodynamics. According to thermodynamics, the decrease in free energy, that is minus delta G, change in free energy, gives free energy is denoted by capital G. And so according to thermodynamics, the decrease in free energy, that is minus delta G, which represents the maximum amount of work done in a system. That is minus delta G is equals to work done maximum. That is W max. Right? And we know that work done in a system or work done by the system is the, so W max we can written as NFE. That is delta G minus decreasing free energy, that is equals to NFE, where N is the number of electrons involved in a reaction and F is the Faraday's constant and E is the electrode potential. So this equation, we can alter this. We will take the negative sign into the RHS. We can write delta G is equals to minus NFE. Right? So this is an equation number 1. Right? Under standard conditions, under standard conditions, when the concentration of all the species is unity, means which gives the standard free energy value. That is, under standard conditions, we can write delta G naught is equals to minus NF. F is a constant and N is the number of electrons involved in a redox reaction. And so here in these standard conditions, under standard conditions, we will get E naught, that is standard electrode potential. So here under standard conditions, when the concentration of all the species is unity, we will get a standard free energy, that is delta G naught is equals to minus NF E naught, where E naught is the standard electrode potential. Right? So consider this equation is 2. And now, according to Ventoff's isothermal reaction, Ventoff's isothermal reaction, means which relates the free energy, change in free energy, and equilibrium constant. That is, according to Redox isothermal reaction, we will get delta G is equals to delta G naught plus RT ln Kc, where Kc is the equilibrium constant and R is the gas constant, right? So here I have taken ln function, and already we have calculated delta G value and delta G naught value, and we know that Kc equilibrium constant. So substitute in this equation number 3. So substitute equation 1, that is delta G, 2 and Kc value in equation 3. We will get what is delta G, that is minus NFE is equals to delta G naught minus NF E naught plus RT ln Kc. What is Kc value? Here molar concentration of metal to molar concentration of metal ion Mn plus. Understanding here? Yes. Mn plus. Now we are going to determine the electrode potential value. So divided by I hope you understand this. Divided by minus NF on both sides, right? I will get E is equals to, so minus NF get cancelled, and you will get a E is equals to minus NF cancel, and you will get E naught. And listen carefully, here on both sides we have to divide this minus NF, not NF, minus NF, negative sign here. So here we can write minus RT by NF, that is minus NF, into ln molar concentration of metal to molar concentration of metal ion, right? And we know that for solid material, the molar concentration of metal is unity. That is, for solid, molar concentration of metal is equals to 1. And when we substitute in this above equation, we will get E is equals to E naught minus RT by NF, same thing, minus RT by NF into ln Kc, that is molar concentration of metal is unity, then ln 1 by molar concentration of Mn plus, because for solid material molar concentration of metal is 1. And now this ln function, that is ln is equals to 1 by Mn plus. So this ln function, yes, for solid material the molar concentration of metal M is unity, that is equals to 1. Then we can write this E is equals to E naught minus RT by NF into ln into ln 1 by molar concentration of Mn plus. Right? Now we can write this ln function. So when we take into the logarithm function, we will get E is equals to E naught minus 2.303 into RT by NF into log 1 by Mn plus. Because here, this is because ln function we need to convert into the logarithm function, just multiply by 2.303 into log. Okay, and we know that log 1 by x formula. So log 1 by x is equals to minus log x. We can write here E is equals to E naught plus 2.303 RT by NF into log 1 by log molar concentration of Mn plus. So this is because log 1 by x is equals to minus log x, right? Or log 1 by m formula, log 1 by m is equals to minus log m. Okay, so this is the Nernst equation for single electrode potential. That is Nernst equation. Here the relationship between electrode potential, single electrode potential and standard electrode potential at particular temperature through a concentration of metal ions. So when we change the molar concentration of metal ions, so the electrode potential also changes. That depends, that is directly proportional to the temperature and molar concentration of metal ions. And also even this electrode potential also affects by the number of electrons, n, valence electrons or valency of the metal. Right? So here where R is the gas constant, we know the value 8.314 joules per Kelvin per mole, and F is the Faraday's constant, that is 96,500 coulombs per mole, and T is equals to standard temperature 298 Kelvin. So when we substitute this value into the above equation, we will get E is equals to E naught plus 0.0591 divided by N into log of Mn plus at 298 Kelvin or 25 degrees Celsius. So this is the Nernst equation at 298 Kelvin temperature. So once again I will just repeat the derivation here. So in 1889 Nernst derived an equation which gives the relationship between the electrode potential, that is single electrode potential, so standard electrode potential, and the molar concentration of metal ion, true and molar concentration of metal ions. So first of all we should consider the reversible redox reaction. That is, metal ions gets reduced by gaining of n number of electrons, gives rise to metal. And we know that according to law of mass action, equilibrium constant Kc we can written as product by reactant. So that is molar concentration of metal by molar concentration of metal ion. Okay. Then according to thermodynamics, decreasing free energy which represents the maximum amount of work that can be obtained from the reaction. right? So that is minus delta G is equals to W max. W means the work done, maximum work done. This maximum work done we can written as NFE, where N is the number of electrons or valence electrons, F is the Faraday's constant, and E is the single electrode potential, or simply we can call it as electrode potential, right? So this negative side we take into the RHS, there is no changes here. Delta G is equals to minus NFE, that is said to be an equation 1. And under standard conditions, the molar concentration, when the concentration of all the species is unity, then we can write the standard free energy value, that is my delta G naught standard free energy is equals to minus NF E naught, where E naught is the standard electrode potential. That means the potential at which the concentration of the solution is taken as unity, right? Then according to Ventoff's isothermal reactions, we will get delta G is equals to, means this Ventoff's isothermal reaction gives the relationship between this free energy and equilibrium constant Kc. Then we can written as delta G is equals to delta G naught plus RT ln Kc, where Kc is the equilibrium constant. That is said to be an equation number 3. Then we know the value delta G naught and Kc value. So substitute in the above equation, we will get minus NF is equals to minus NF E naught plus RT ln molar concentration of metal by molar concentration of metal ion. And we need to calculate the single electrode potential value E. So divided by minus NF on both sides, LHS and RHS. We will get E is equals to E naught minus RT by NF into ln function. So this is a ln function. So that is molar concentration of metal by metal ion. For solid material, molar concentration of metal is taken as unity. That is taken as 1. So E is equals to E naught minus RT by NF into ln 1 by Mn plus. And so E is equals to E naught, this ln function is taken as logarithm function by multiplying 2.303. Here this is 2.303. 2.303 into log 1 by Mn plus. So this is a Nernst equation for single electrode potential. So this is taken by the log 1 by x formula is equals to minus log x, or log 1 by m formula. You take the denominator terms into the numerator, the sign changes here. So minus plus. And when you substitute the R, T and F value, we will get E is equals to E naught plus 0.0591 divided by N into log of Mn plus at 298 Kelvin temperature. Yes. So and then next we are going to determine the cell potential or electrode potential of the galvanic cell by using a Nernst equation. By using this equation, we are going to determine the electrode potential of or EMF of the galvanic cell, right?